Okay, now we have a situation where a mass rests on an incline, 37-degree incline, same incline we've used previously, but the mass isn't given. So all we know is that the force of gravity, and this is a vector force, is mass times the vector gravitational acceleration. Gravitational acceleration being in the vertically downward direction, mass being a scalar, these have the identical direction, which is vertically downward. If we choose our coordinate system so that the x-axis is along the direction of motion of an object on this incline, and y, of course, being perpendicular to that, and this is the choice we always make for an incline unless there's a really good reason to make some other choice. Analyzing this thing with any other coordinate system is unduly stressful. Okay. And again, that's because we have no motion in the y direction, okay? And all our motion is in the x direction. So we have y equilibrium, and for the x direction, well, we have whatever we get. Okay, well, we immediately replace this gravitational force with its components, its x and y components. And without going into it, we have a 307-degree angle here, giving us an x component of the gravitational force is mg sine 370 degrees times I. The 0.6 mg is correct, but the sine, of course, that's the cosine, and this is the sine. I was kind of moving through that quickly and wrote these down incorrectly. Okay. So there we have it, and the sine of 307 degrees is about positive 0.6, so we get 0.6 mg times I. The sine of 307 degrees is about negative 0.8, very close to negative 0.8, so we get negative 0.8 mgj. And now we can redraw our diagram. At the point of redrawing, I didn't have any of the colored vectors indicated. I only had the diagram with the y component and the x component indicated. Then we went on and we sketched our friction vector. Now, why did we sketch the friction vector in this direction and not this direction, or at some angle, vertical or whatever? It's because friction acts in the direction opposite motion, so that any motion on this incline will either be down or up. Now, if the motion is up, the frictional force will be down the incline. If the motion is down, the frictional force will be up the incline because the frictional force resists the motion. Well, in this case, it's said that the object is sliding down the incline. It's sliding, so it's moving. It's not stationary. So that the frictional force will have to be in the direction up the incline. So I just drew a frictional force up the incline. At the moment, I don't know the details. I mean, I do, the details are given, so I could know the details. But when I draw this, I don't even bother, I don't even need to bother thinking about whether this force is bigger than this one, or whether they might be equal, or this force bigger than this one, okay? I just draw a frictional force. Now, it's okay if I look at my information and I make some sort of an estimate of the frictional force and try to draw the vector about right. But the point is, whether I draw the vector correctly or not correctly, as long as I have it in the correct direction, it's going to represent the force, and I'm going to be able to use it in my analysis. And if it's actually bigger than this, well, that's going to come out of my analysis. Okay. Then at that point, I didn't have this drawn in here. You see where we're going with it, but at that point, I asked the question, do we have equilibrium in the x direction? Well, it's possible that we do. Okay, if this vector is equal and opposite to this one, and those are the only two vectors acting along the incline, then we would have equilibrium, because equilibrium means zero force, zero net force. And we would have zero net force if these two were the only two forces and were equal in magnitude, opposite in direction. Otherwise, we don't have equilibrium in the x direction. We don't know yet. We haven't finished the analysis. So anything is possible, but it's not necessary that we have equilibrium in this direction. Okay, what is necessary is that we have equilibrium in the y direction, because if we don't, there's a net force in the y direction, so the object is either going to come up off the incline or go down through the incline. And we've excluded those two possibilities just by assumption. We assume the incline is strong enough, we assume there's no force that causes the object to rise up off of the incline. Okay, in that case, the forces that I had listed at this point before I drew in that blue force, would not have given us y equilibrium, so we knew that we needed additional forces for y equilibrium. This was the only force in the y direction, and it's not zero. The y gravitational component of the gravitational force is absolutely definitely in this situation at this angle not zero. So we know we have to have another force. And the only source for that other force, unless we make up something, is the normal force exerted by the plane as the plane bends slightly, maybe under the influence, or compresses slightly, and either way reacts in an elastic manner and pushes back in a direction perpendicular to the incline, and that force is then what we call the normal force. So now we've got our normal force, we've got our gravitational component in the y direction, and we can begin writing down or summarizing what we know about the forces. So, in the x direction, what do we know? We know the x gravitational force is 0.6 mg times I, and the frictional force is whatever the magnitude of the frictional force is times negative I. So F fric without the arrow means the magnitude of the frictional force, and it's going to be in the direction opposite I by the given condition that the object is sliding down the incline. Okay, and then what about our y force? Y forces, well, there are just two of them. We have the gravitational component, which is negative 8 mg times j, plus the magnitude of the normal force times positive j, because this has to be in that, among other things. Well, actually we don't have to make any assumptions. So we'll just say this is F norm times j. Okay? Now, we know we have equilibrium in the y direction, so that the sum of all our y forces is zero. So y equilibrium implies zero net force in the y direction. The net force in the y direction is the sum of all the forces acting in the y direction. That sum has to be zero. Well, the only forces are these, so they have to add up to zero. So negative 8 mg times j plus F norm times j equals 0, which means F norm times j equals 0.8 mg times j, so that F norm has to equal 0.8 mg. Okay? Now, we look at the x direction. Or maybe we just kind of continue on. Once we know F norm, we might notice that we can calculate the force of friction, because, as the problem said, it said the frictional force has a magnitude that's 20% that of the normal force. Okay? Meaning, of course, if you put it in standard terms, the coefficient of friction is 0.2. Okay? The frictional force is always some coefficient multiplied by the normal force between the two surfaces that puts the two surfaces together. Okay, yeah, okay, I'm not going to say more about that. Okay, so, and 0.2 times the normal force being 0.8 mg, gives you 0.16 mg. So, if we look at our net force in the x direction, it's going to be this force plus the frictional force times negative I. Magnitude of the frictional force times negative I. That's going to be 0.6 mg times I plus 0.16 mg times negative I. And of course that adds up very easily, give us 0.44 mg times I. So our net force is 0.44 mg times I plus 0j. Because again, we have automatically, we have equilibrium in the y direction, which means zero net force. Follows that our acceleration is F net vector, our acceleration vector, our vector acceleration, is the F net vector divided by the mass. And if we do that, if we divide the I component, 0.44 mg, by the mass, we're left with 0.44 g. And of course, our J component of the net force is 0, so we're going to have 0 acceleration in the J direction. Okay, that's pretty much it. A couple of other things that we can say, though, is that if there was no friction, then our net force in the x direction would just be 0.6 milligrams times milligrams, mg times I, times the I vector, and the acceleration would then be 0.6 g instead of 0.44 g. The 0.16 mg that we get here reduces our acceleration by 0.16 g, and that's the acceleration we end up with.